So today we are going to take a kind of a real shallow dive into frequency domain analysis. So you're going to figure out first, well, what do I mean when I talk about frequency domain? Then we're going to talk about Fourier transforms, a little bit about spectral analysis, and then we'll end up talking about wavelets. So by way of motivation, so far in this class, in the first 7.5 weeks, we've been focusing exclusively on measuring some entity. It might be a scalar, it might be a vector of things that are indexed over time. So like right here, right, we've got a time series where time 1, it was some value, time 2, time 3, time 4, et cetera, and we end up with this. We can really think about this as comparing changes in some sort of amplitude or displacement over time, right? So just imagine, back to this figure, if we've got a 0 bar here, you could think of this as just measuring some sort of deviation away from 0 at each time step, right? Rather than that. In the frequency domain, we're going to instead explore how this amplitude changes not with time, but with frequency. And this will become a little more clear as we move through this material. So first thing to talk about when we think about frequency domain is JeanBaptiste Fourier, who was a French mathematician and a physicist. And really what he was best known for is some early work he did on heat transfer in physics. And he is actually the one who first described what we all refer to as the greenhouse effect. So, basically before this, we were even a country. He had figured out that greenhouse gases were a thing and that you could warm up a planet by having greenhouse gases. And the issues that Baptiste was running into was he was dealing with the heat equation. And if you remember this from physics, it's not simple. And basically what it amounts to is solving a whole bunch of partial differential equations. And solving PDEs can be very tricky, and especially when exposed to a whole number of boundary conditions. So what he has a situation where he's got a problem and it's really hard to get to the solution. Okay, that's basically his issue. So what Fourier figured out was, well, what if I started here with my problem, and instead of going straight through to the solution with a via some really hard route, this is climbing Mount Everest straight up. What if we just sort of circled around it slowly and got to the top? So what he figured out is, well, what if we had some function f of t and some inverse, I'm calling this f hat of t, such that we could move our problem into some transformed space and then in a much easier path, get to a transformed solution, and then map that back on to our real solution. So that's essentially the essence of Fourier analysis, is figure out this f of t and figure out its inverse. And then you don't have to deal with this really hard path here. You can take a much easier route through here. Okay. So what is a Fourier series? Well, it's a set of periodic functions. So we're thinking things like sine waves here, and they involve complex numbers, or can. And basically the idea is that you can describe any time series as some sort of sum of sine waves. And here initially you're thinking about this as an infinite sum. So this sum is going from k up to infinity. But in practice, this can be relaxed. You won't need infinite number of sines to do this. You need a much smaller set. So you can imagine k is the number of different waves we have. Then ak here is the amplitude of that set wave. Here's something about the frequency, and then they can be different phase. So you can have sine waves that are really big, or some that are really small, and some that have really long periods, or some that have really short periods. But the idea is by stacking up all of these different sine waves, you ought to be able to come up with some relatively convoluted shape. Okay, so in a finite example now, let's consider one of these. So here's a case where I've set capital K to 5. And we're going to look at 5 different sine waves where the amplitude is 1 over k. So the first time it'll be 1, that's going to be a half, a third, a fourth, a fifth. And the frequency here is going to change with k. So as k goes up, the frequency is going to go up. And we're going to phase shift this by k squared. Okay, so here's an example of what that would look like. So these colored lines here are the 5 different sine waves. So you can see here's one where k equals 1. It's got relatively long wavelength. And then here's one where k is getting much bigger and it's relatively short. And see the black line I have here is the sum of all the colored lines. So you can see that, right? This does not, the black line in and of itself doesn't look like a sine wave. It's regular in that there's a repeating pattern here, but it's irregular in its shape. So just by pulling sine waves up and down this way and stretching them this way and maybe even moving them a little bit, you can add these things up and describe all kinds of different shapes here, right? So with 5 waves, I described a pretty complex pattern. You can imagine if we had 10 or 20 or 100, you could make this look really wild. And so for those of you, I'm going to presage this a little bit. For those of you who've studied GAMs at all, and where GAMs have basis functions, it's the same idea in a GAM, is that you can add in a number of these different basis functions and you can start to describe weird looking patterns like this. Okay, so the idea here is that, right, the frequency is changing as the amplitude is changing as well in this case. So going back here, right, one of these has really high amplitudes, 1, and then one of the smallest one in here is down around 0.2. So as k is going up, the frequency is, or sorry, k is going up, the frequency is going up, but the amplitude is decreasing. So I'm going to jump over here real quickly to this animated example. So here's f now, right? So here's a signal we're trying to describe. And if we add in a whole bunch of these cosine and sine waves in blue, you'll see that this is going to stretch here in a minute, right? So now you can see all these things, and I can't pause this because it's a GIF. But right, there was a low period wave. So here's your amplitude by frequency, just like the figure I showed you a moment ago. I'm going to wait for a second, see if it'll, oh, there, it just finished. Okay, so I'm going to rewind this one more time so you can see this again. And as this plane shifts out, it's most informative, just coming up here in just a moment. Okay, right here, as you stretch this out, so now you see there's 1, 2, 3, 4, 5, 6 different frequencies, and the amplitude of each of these is different. It's highest here. Okay, and so by basically constructing those, you can see how that works. And I'll let this finish again so everyone can see it. All right, I think that just ran through. Okay. Okay, so that's a Fourier series, right? So what's a Fourier transform? Well, Fourier transform is where we're going to make use of Euler's formula. And Euler's formula says that we can have a cosine in real space, and we can have a sine in imaginary space, and adding these two up is e to the I 2k pi. So it's this argument inside here becomes the exponent with an I up there. So this is just Euler's formula. And you probably saw this a lot in introductory calculus. So the idea here is that we could write a Fourier transform in terms of Euler's formula. So here's Euler's bit right here, where now we've got this additional k piece. And here is essentially integrating from minus infinity to infinity over all of these different functions multiplied by Euler's product. So this is essentially an inner product of some function that we want an Euler's number here. This is going to make a little more sense. So this was all done in continuous space, right? We're thinking about a continuous time integral here. Now we can think about this in discrete space. So now instead of integrals, we're dealing with sums. And so here we're going to run from 0 up to some n minus 1. And this is going to be the value at time t times this Euler exponential here. So if this bit right here is essentially, well, depending on what you get, this is going to cause this to either shrink or pull. It's either going to grow up like this or it's going to collapse down, depending on the values of n and k. Okay, so if we're going to do this in R uses something called fast Fourier transform. And there's a function in R called FFT, which stands for fast Fourier transform, which basically returns the amplitude at each frequency. So several slides ago, you saw I had amplitude as a function of frequency, and that's what this will do. So if you have some time series, x of t, and you pass it to this, you're going to get the Fourier transform of that. And oftentimes people normalize those by the length of the time series just to make it behave nicely. So here's that x of t that we just had. So what you're seeing is that at a frequency of 0, 1, there's hardly any amplitude. Then at 2, we have a really large amplitude. Then it's small, then it's broad, then this is sort of decaying. And then once we get out past 10, these are essentially 0. Okay, so now we've got a way to describe the transform, but we need a way to get back. So this is our discrete time thing where we're going to sum from 0 to n minus 1. Here's the actual time series. Here's this imaginary value problem. Well, the transform of that is essentially the inverse, right? So now we've swapped these two out from one another, and this is now e to the I, not e to the minus I. So if you can calculate f of k here, you can use this formula to recover the original time series. So this was Fourier's kind of bypass of that hard problem. So here's going into transform space. You solve that to get to here, then you go back. Okay, so to do that in R, you basically can just write a little loop to do that. So here I'm going to define this I to be literally I in complex, the number I, right? Square root of minus 1. And the way you can do that in R is to say complex, and it's got nothing is real, and the imaginary part is 1. And I'm only asking it for one number. Then I'm just creating an empty vector here. And I'm creating an index where we're going to go from, k is going to go from n to 1 to, or so 0 to n minus 1. And we have our f of t that we got back here. Right, so we defined f of t with the fast Fourier transform. And now we're essentially writing out this formula right here in R. So that's this. So we'll just loop through our index, and it's going to be the sum of that times e to the I times 2 times pi times k times t normalized by n. Okay, so here was that original sine wave, remember? Or no, I'm sorry, not a sine wave. This was the function of 5 different sine waves. It's the gray line, and this dotted blue line is what we get if we take the Fourier transform of it and then just iterate that code here to get x of t. So now I'm plotting the overlay, and you can see that we did it. We recovered exactly what we wanted to. It turns out that you can do that shorthand in R by this. You don't have to write that little loop or your own function to do hand. The fast Fourier of this is now the Fourier transform. So if you pass the transform to f of t and then say inverse equals true, it will give you the inverse Fourier transform. So I of t should be our original time series. And in fact, that works as well. So now the gray is our original series, and the red dotted line is what we got when we used the FFT inverse. Okay, any questions on drinking from a fire hose with respect to Fourier transforms?
How do you decide, Mark, when to use that method for a time series? Like what characteristics?
Yeah, so that's a really good question, Jessica. And honestly, I should probably do a little better job of motivating this in the beginning. There are certain fields of science where people really enjoy working in the frequency domain much more than the time domain. And those are primarily physics and applied math, but that extends into things like biomechanics. So I have a very good friend who did all of his PhD work in biomechanics. So he was trying to figure out like how crickets can jump so high and this sort of thing. And and people who work in like medical professions, working on like EKGs or ECGs, a lot of them tend to work in frequency domain, because a lot of what they're thinking of is they actually have signals, right? You have some machine and there's an input signal coming in, and on the backside, there's some other signal that comes out. And you can imagine like an EKG, right? Where it does these things and then you get these spikes, and it gets these spikes. So they're interested in describing sort of, they don't really care exactly what the amplitude of that spike is at any particular time. They're trying to describe the overall shape of that thing more so than what the specific value is at any given time. So it just appears in like in the work that we do in ecology and environmental science, almost no one is doing this. Okay? I mean, it's really rare that I see anyone doing it. Now, later when we start talking about wavelets, that starts to show up a little bit more. And I've seen those applications in ecology and environmental science for sure.
Hey, Mark, Michelle got kicked off. Do you mind letting her in again?
Sorry, yes. Thanks for being a friend there, Brielle. Yeah, I probably should have given you all my cell phone number and you could be texting me and being like, I'm stuck. So maybe we've got, oh, Michelle's back. Okay, good. Sorry, Michelle. All right. Any other questions on Fourier? But this is something that I would encourage you all to play with sometime. Just go ahead, like simulate some time series and pass it to FFT, and then do the inverse and see if you can basically figure out the solution. And it should work in theory. Now, of course, I made this relatively stylized example here by stacking up some. If you can imagine, we added a bunch of noise on this. You're not going to recover the exact thing, but it'd be really close. And if you wanted to use more than 5 series, like 10 or 20 or 50, then you get really close to doing that. Okay. So let's talk a little bit about spectral analysis here. So spectral analysis is just a general term, and it refers to sort of a way of decomposing time series into their basis frequencies. And so let's think about a linear regression model for a time series x of t, where we're going to use cosines and sines as a predictor. And this is essentially akin to what we did earlier in the class when we talked about seasonal models. And this was one of the methods that we showed you as a way to sort of model seasonality in time series. Same idea. So here we've got an intercept, and now we've got a whole bunch of terms, and we're going to run from essentially half of the data up -1. And each one of these is going to have, this is essentially the beta, the regression coefficient, AK, and here's BK, and this is a sine wave, or cosine, sorry, and this is sine. So given that, we can construct something called the periodogram, which is the contribution of each of these frequencies. So remember, A is the regression coefficient for cosine, and B was for sine. And so at any one of those Ks, we just square those up, and we can ask how important are either one of these waves at a particular frequency, right? Because here frequency is changing as K changes. That's inside this bit here. So if you want to do this in R, you have a couple of options. Spectrum is the function, and you pass it a time series. And then you have 3 options for your arguments. You can either tell it, I want to show the results in log space, I want them in normal space, or I want them to actually be shown as intensity as measured by decibels, which is essentially a log scale as well. So here is a periodogram for that original xt. And the way these work is this one I'm showing it is in decibels. So it has decibels on the left here. And then here are frequencies. And so the idea is you're looking for sort of power, you could think about it, or intensity as measured here by decibels with different frequencies. So remember, you have to take the inverse of this to think about a wavelength because these are frequencies. So 1 over this is 1 over 0 is really big. So this is 10, right? This is 2. So what this is telling us is that that time series, that kind of smooth, stacked up sine waves, shows a lot of, let's call it, for lack of a better word, it has a lot of the attributes of low frequency waves. And then as you trickles down here, there's very little evidence that you have all this high frequency variation. And here's that same plot where we haven't done anything to the y-axis here. This hasn't been transformed at all. So this is just in a natural scale. So now frequency here is shown out, and you see that really all of the dynamics in that time series are happening at relatively small frequencies. And that once you get out here, they're essentially gone. I think I did another one. Nope. So again, that function to do this in R is just spectrum. Okay, it turns out that there's a link between the spectral density of a time series and AR models. So everyone here now is quite familiar with autoregressive models. We've been focusing a lot on just AR1 models in this class, but you can imagine, right, we could have AR10 or something like that, where we've got 10 different terms out here. The spectral density of an autoregressive process can be set up to be essentially a sum. So here's the variance of these errors. And for each delta t, so time step 1, 2, 3, 4, you divide by 1 minus the sum of a whole bunch of, here's our, this bit right here is our essentially our Fourier. So we can stack up a bunch of these, take 1 minus those, square them, and that will give you the spectral density. So it turns out that you can model any AR process as this form of Fouriers and go backwards. So if you actually wanted to simulate or figure out the spectral density of something like this, you could use a super high order AR model. Okay, so spectral density is kind of neat because you can basically figure out where your kind of the major variation is happening at which frequency or wavelength. But the issue is that it really only works well for stationary time series, like an autoregressive model, ARP. And it will also work really well if you've got periodic signals corrupted by noise. So right, we had that sort of sine wave. So imagine like the Lake Washington temperature data, where we looked at those earlier in the class, and they really do have a fairly strong seasonal aspect to them. But some summers are warmer than others, some winters are colder than others, so it's not a perfect sine wave. There's definitely some noise around that. Spectral analysis suffers, though, when dealing with most real-world data, and especially in environmental sciences where we have a lot of gappy data. And in general, it tends to be biased. So for a lot of the systems that you all and I would work with, spectral analysis is only going to get you so far. Now, if you've got an animal hooked up to an EKG and you can just let that thing run, spectral analysis will work great for that because there's not going to be any gaps in it, you know, unless you have some power outage or something like that. And you can just let that thing run for a long time. So you get a lot of signal. There's not a lot of noise in there, and they don't tend to be gappy or anything like that. Okay. This issue, that this kind of the buts here, motivates something called wavelets. So the idea here is that when we talked about Fourier transforms in spectral analysis, we had a set sine wave with a set frequency and amplitude, and then we just added a whole bunch of those up. But there's situations where you can imagine that sine wave is being kind of pushed and pulled. And I'll give you a real world example. The rotational speed of the Earth is not constant over time. So the actual length of a day varies a little bit. We always think it's 24 hours. Well, it's kind of 24 hours plus or minus a little bit. So it's actually, if you tried to model the length of day over time, that it would look a lot like a sine wave, but that thing would at some point be pushing and pulling a little bit. The frequency would actually change. So for non-stationary time series where that sort of thing is happening, we can use this idea of wavelets. And a wavelet is what it is. It's a small wave, okay? And so when we think of small wave, we're really going to focus on a specific time and at a specific frequency. And this will become a little more clear here in a moment as we think about this. So let's think about just general decomposition. In regular space, when we're thinking about a time series, at each moment, at steps of time, we get some information about the time series, but we don't know anything about the frequency. So telling anything about it, right? If I give you a time series AX of t, at each point in time, you can tell me exactly where that amplitude is, but you know nothing about the frequency. In Fourier space, you know lots about different frequencies. Here's something 1, 2, 3, 4, etc. But you know nothing about where you are in time. In wavelet analysis, we're going to combine those bits. So in wavelets, we know something about changes in frequency. And then we also know things about changes in time at different frequencies. So this would be a case where here we've got over this entire time period, there's one frequency we're considering. Then here there's 2 that were divided in half. Then there's 4, 8, 16, 32, etc. So we're going to be adding up these different groups. So you can think of, okay, these down here are really long waves, really big things. And these up here are really small waves. And we can think about looking at really small waves at this point in time, and this point in time, and this point in time, right? So we're going to do that a lot here. But down here, we're only going to consider one wave over a whole time period. And the reason we do that is because these long wavelength periods tend to persist in those manners. It's really rare that you'd have something that had a really long wavelength, then all of a sudden it went and then got really long again. But these short frequency things that go up and down, those may stretch and pull a lot in there. So where the frequencies are high, we want to be able to check at multiple points in time to see, is that frequency changing? When the frequency is really low, so you get these really long waves, we don't have to check that very often. In fact, we'll just do that for the whole time series. Then we'll make the frequency a little smaller and we'll check twice. Then we'll make it smaller yet and we'll check 4 times. Then we'll do it 8, right? So the idea is that we're going to look at different frequencies and at different periods of time. So you can think about a moving window essentially moving through a time series. Or we'll take the entire time series, then we'll cut it in half, then we'll cut it into fourths, and in each of those we'll examine what's going on. Okay, so what is a wavelet? I said, well, it's a small wave. Well, basically we define a wavelet, and oftentimes they're written using the Greek letter psi, and they can be indexed at some t, and there's essentially 2 parameters of interest here, and I'm calling those sigma and tau. Sometimes you'll see them just simply written like a and b. And the idea here is that there's a scaling function out in front that's a function of sigma. And then you've got a function, this wavelet is a function of t and tau and sigma. So tau basically tells us where we are. It just shifts this thing left or right. And sigma here is a scalar, right? So if sigma is big, this whole quantity is going to be small. And if sigma is small, this whole quantity is big. So this tells us if we're talking about really long things or really short things. So by adjusting tau and sigma, we can adjust our wavelet to be something that looks really big or something that's really small. And we're only going to focus on relatively local pieces of the time series at a time. Okay, so if you think about that, right, this is a case where this one hasn't been shifted at all, and it's got a relatively small sigma. Then you could think about, well, t equals 0 might deal with this one, and then t equal 1 might deal with this one. Here's t1, then you might have to do like half, half. This would be 0, 1/2, 3/4. Did I do that right? Quarter, half, 3/4, 1. And then and then sigma, as you go up through here, we're making sigma larger and larger and larger, so this thing is getting smaller and smaller and smaller. Okay. Wavelets have two properties. Number one, they have to go up and they have to come back down. So that if you integrated from -infinity to infinity, it's 0. So the idea is that you've got some mark here. The amount of space above this line is always the same as it is below. Okay, so they're positive to negative space, they're complementary. And wavelets have a finite sum. So if you integrate it over that whole interval again, the absolute value of that will always be less than infinity. So that basically means they're in, it's not a, right, if this were a sine wave, the answer is no. Right, those will, so that won't work. Okay, so how are wavelets defined? We talked about this a little bit with respect to this. So usually we talk about these with respect to some things called scaling functions. And the scaling functions will either talk about, number one, dilation. So that is, you know, is this time interval we're going to think about really big? Is it t? Is it 2t, 5t, 10t? And the translation is basically where it is. So that's like the tau bit. Are we over here? We over here? We over here? We over here? So you could stretch this thing, and you can shift it. Okay, so more generally, we can think about this wavelet as having some index for dilation, that's this j, and then we can have k describe its translation, right? So this is going to describe how big this thing is, what's the frequency, and k is going to tell us where we are as we look at it. And then this bit out here is just a normalization constant to make it behave well. Okay, so all right, that's fairly abstract. Let's try to put this into practice here. We're going to use some scaling functions that look like this. So our wavelets are going to be a sum, and they're going to be a finite sum. K is going to be relatively small. And then we have some coefficients here, which is essentially called a filter. And then in this one, we're going to have 2 times x. Remember, this is our observed, and this is our translation. So this is a fixed length wavelet that now moves along through a time series. And as k increases, this is going to get smoother and smoother and smoother. So when k is really small, it's going to look like a square wave, for instance. But as you crank k up, it'll get really smooth and look like more like a sine wave. Probably the most common wavelet around, and I think was one of the first described, is called haars wavelet. And this was first described in like 1910. Okay, so a lot of a lot of mathematics has a very old history. Wavelets is a relatively new discipline. And since then, there have been a whole number of other wavelets that have popped up, and we'll show you some examples of those. So in haars wavelet, k is going to be 1, C0 is going to be 1, and C1 is going to be 1. So here's our general formula for a scaling function. So if you plug those values in, you're going to get something that looks like this. So the only function that will satisfy this relationship is that the wavelet gets a value of 1 if t is between 0 and 1, and it gets 0 otherwise. Okay, so this is just a hard square wave, and I'll show you an example of that. So that's what this looks like. It's 0 everywhere until it's between 0 and 1, and then it gets a value of 1. and then it's 0 again. And time here in this case, you can actually imagine is going to move. So you can imagine this thing actually starting somewhere over here, and we're going to pass this thing, this really funny square wave, through a time series and see how that maps onto the observed values. Okay, so we talked about dilation, right? This ability to stretch the thing. So for psi of 2t, this is going to be 1 if it's between 0.5 and 0 otherwise. And for the translation, it's going to be 1 if you're greater than 1/2 but less than 1 and 0 otherwise. So here's an example of what that looks like. So here's one where at 2t, right, this one here, is 1 if it's between 0.5, and then 2t minus 1 is 1 if it's between 1/2 and 1. So here's our first one, 2t, that goes, it's 0 everywhere except in this region. That's down to 0 here. And that y at 2t plus 1 is 0 everywhere, but it's 1 here. Okay, so now we have something called the mother wavelet, which is basically the one that's going to be at the bottom of that stack. It'll be the one that we only have one version of, and we apply it to the entire time series. So the way you get these to work is you can difference those scaling functions. So the way you have this little pre-multiplier here, which is just -1 raised to k. So when k is 0, this is going to be 1. When k is 1, it's going to be -1. When k is 2, it'll be 1. So it's just going to flip-flop, right? -1, 1, -1, 1, -1, 1. And then we can march this thing through the time series. So that's going to do something like this. So that's what the mother wavelet looks like. So now you can see that this looks a little bit like a wave. It's just very square. And you can see that it's symmetrical, right? There's the same amount of area above 0 as there is below 0. So the summation of this thing is 0, and it's finite. You could actually calculate what the area is there. So we can create child wavelets from that mother wavelet by just increasing the dilation and translation. So if we multiply here, we'll make this bigger. And then if we adjust k, we can move that thing along our time series. And then again, we have this normalization constant out in front. So in a basic Haar wavelet, j is 0, right? So this goes to 0. This whole thing becomes 1. This is 1, so it's just psi of t minus k. If you now set j equal to 1, you get this daughter wavelet. So you'd have the square root of 2, right? That's 2 to 1/2. 2 to the 1 is 2. So here's square root of 2 times a wavelet that has a dilation of 2t and a translation of k. Okay, so here for the daughter wavelet, then we've got this little bit here again, where this will just make this thing switch from -1 to 1 each time step. But now we've got a little smaller amplitude, and we've got a little larger dilation, and we're able to shift this, right, as this moves around. So there's a daughter wavelet of Haars. So now we've essentially got, this does this in the same step here, it makes 2 of those cycles rather than just 1. But again, this wavelet has the same amount of area above 0 as it does below 0, so it fits our description. And you can imagine doing this again, so we'd have this thing go up and down 8 times in this region rather than you go 2, 4, 8, 16, 32, etc. And then this thing kind of slides through the time series. Okay, so that's Haar's wavelet. That's this rather square wavelet. There are other forms, and largely these have sort of arisen in the last 50 years. Here's one called the morlay wavelet. This one is a lot more smooth, right? It doesn't have that square aspect that haars did. But same thing, this is essentially the zero line here. There's equal area above and below zero, and it's finite. There's the Mexican hat, looks kind of like a sombrero, right? That's the idea with this one. But same thing, it's asymmetrical above zero, but there's still the area below this line is the same as this area above. So that's symmetrical. Oh, I thought I had a figure. There's a relatively famous mathematician, a French woman named Dobschies, and she created several wavelets. And when I was taking a course from Don Percival, who's at the Applied Physics Lab here at UW, he's kind of one of the wavelet gurus. He was explaining that one of the wavelets that Dobschies had described is called the least asymmetric. This is a total side note, but I had a question for him. I was like, why didn't she call it the most symmetric? He had no answer. I don't know why. This is fun. This mathematicians are funny people. So yeah, if you look up least asymmetric wavelet, you'll find that. Okay, who on earth does this stuff, right? I was, back to Jessica's question earlier in the class, like why on earth would you do that? Well, wavelets shows up a lot in audio and video compression, right? So if you have some massive amount of sound or video, that's often described, right? All that stuff as amplitude and frequencies. That's the way we, I speak at a particular frequency for the most part. I can get louder, softer. But if you think about that, that's just something that you're tracking over time or space for that matter. So if you could do a decomposition of this, you could use wavelets to describe how something changes with only a subset of that idea. So remember back to when we were talking about DFA, and the idea was we had all these time series and they had all this variation in them, but actually we could use a few kind of underlying states to sort of characterize most of that variance. That's what's happened in audio and video compression. So they pass filters through there, and they can use a few different filters to essentially recover the original thing. So right here's an example of a JPEG. So here's what the original object image looks like. And here's a low pass filter that comes through here. And each of these are essentially different forms of wavelets. And they're picking out prominent things. Like this one's really focusing on sort of the hard outline of this tower here and some of these other turns. This one's grabbing some of the bits on the bricks on the side. This one's starting to see that. Okay, so you pass through here. Then they shift up to a different frequency, pass the same wavelet through there, and then you could imagine this is a highly stylized version, but the combination of these you could essentially recover something like this. So that's what happens when you have JPEGs, right? All the computer knows is there's a bunch of intensities at certain locations, and by essentially stacking all these things on top of one another, you get this. All right, let's talk a little bit about wavelets in R. There's a package called Wavelet Comp, and that package uses the Morley wavelet by default. And as far as I know, I don't even think you can change that, although it's been a little while since I've used that, so maybe they've updated it. So let's look at the Lake Washington temperature data set. You'll recall that this is a fairly regular looking sine wave, but it definitely, the amplitude changes in some years, right? Some years it's hotter, some years it's colder. So I'm just going to define a variable based on Lake Washington temperature data set. Call this thing, and wavelet comp needs a data frame as an argument. You can't pass it a vector. So here I just created a data frame that's only got one column in it. It's just temperature. Okay, so then the function you use is called analyze wavelet, and it takes a few different arguments. So it's funny because you have to pass it the data frame, then you have to tell it the column name you're passing it, because it will only work on one time series at a time. This says I don't want any detrending because my data don't have some funny trend in them, the Lake Washington. You have to specify essentially the delta t in sort of frequency, and so this is 1/12 because it's monthly sampling. If it were hours, we'd call this 1/24. Something that was quarters, we do 1/4. it's asking for a lower period, which is sort of a base where it's going to start. And the default is to take twice what your sampling interval is. So that's 1/6. And this has essentially a resampling algorithm associated with it. So you can actually estimate sort of confidence in your thing. So this also has an argument for n sims, which is essentially you can think of as a number of bootstrap samples, and false. And the reason that there's this funny text on the slide is there's this function, as it's doing this, marches a scale bar across. So if you want to play around with this at home while you're sitting there, and I cannot suppress that anyway. So that's what this really weird stuff is going on at the bottom of the slide. It's Markdown trying to grab a dynamic thing and make it static. Okay, so what does that result in? Well, once you've done this, so I've assigned this object, which is the wavelet analysis of this, you can display the results using this function wavelet transform.image. Okay, so this is now time. So we have many years of Lake Washington data. So it's about 400 months, 396, I think. Here's period, which now is essentially the wavelength. So these are very small, these are very large. And here's the power of that. So when this is yellowish color, there's not much information happening there. When it's really dark, there's lots going on. It's really indicative of that. So what this is saying is that for this rather generic time series that doesn't actually have a lot of structure in it, there's a lot of wavelet power at a period of 1, which is essentially a year. So every year this is repeating itself. And so it says, yeah, if you had a sine wave that was roughly 12 months long, it would look a lot like this. And the reason you get this sort of bullet shape on here, this kind of funny contour, is that essentially what's happening is we had a time series of temperature, and the way the wavelet works is it's essentially, you can imagine wrapping that time series around a circle, and you're going to pass, that wavelet is going to run around the circle. But it has to start at the beginning and start at the end. And for these, where the wavelet is relatively long, you don't get all of this, right? You need some information at the beginning and at the end in order to pass this. So you lose information at the end. So it's sort of like when we were talking about doing autocorrelation, when you had after a while, you're only comparing fewer and fewer values. So that's what's going in. So where do people use this in environmental science? Well, this one was a fairly generic example just to sort of demonstrate what's going on. But people are using this to talk about changes in like ocean temperatures off the coast here, over where you can imagine years, months and years. And you can see that in certain cases, there are real times when power spectra really jumps out at you, that something is really changing heavily. And then it will maybe shrink down again at a certain amount of times. And you can imagine doing this by latitude as well. So in a multivariate space, these become much more interesting, and they can tell you sort of about changes at particular frequencies at particular times. So if my earlier example of the rotation of the Earth was changing, if you had the ability to actually measure that, now mind you, it's changing in like milliseconds or micro, I mean, it's tiny amounts. But you would see that at certain times, these might go kind of yellow and then they would become purple again. And things up here might start to pop out as yellow or purple, as that sort of the shape of this thing is changing with time, because it's not regular. It's designed to be something that's being pushed and pulled and even changing in amplitude for that matter. Now, that said, this package worked on a Morlay wavelet. If you passed a different kind of wavelet through there, you would expect to get different results from this. But in general, that doesn't have a huge influence on what's going on. And if you're interested in learning more about this, I definitely would point you towards some of the information about wavelets. And they talk about some of the wavelets forms are designed to do very specific things. If you're looking for specific changes in a time series, then you should use a specific wavelet. But like I said at the outset there, in environmental sciences in general, I don't see a lot of people doing wavelet analysis. It does show up on occasion, but particularly because oftentimes you actually need a relatively long time series, right? I mean, if you had 20 years of data, that's not very much to pass of several wavelets. You wouldn't get very far through these frequencies and you'd be done. Because with only 20 years, you can't have something that's, you know, centered on 0 and then has 10 units on either side. You just it'd be up and over. Okay, so the inverse, remember we talked about inverse Fourier transforms, the ability to go backwards, and for discrete ones, that was really fairly simple. Like we just did it by hand, we just coded it up in R. Doing the inverse wavelet transforms is going to get you to integral calculus really fast. There's no other way around this. So the software that does this is, you know, optimized to do so. But the issue here is that you essentially have, now that's funny, I switched notation, right? Originally I had these as in terms of tau and sigma. Now I'm just referring to this in terms of A and B. So you have the inner product of this, essentially some sort of function that we don't really know, and the wavelet. That inner product is being integrated then twice over the basically the dilation and the translation. Okay, so in R, you can use the reconstruct to get the basically that inverse of the wavelet transform. So the black line here is the Lake Washington temperature data that I've now standardized. It's a z-score. And the red is the inverse wavelet fit, if you will. So by passing, so the results of this going back into the time domain from this combination gives you this sort of red line here. So that worked pretty well all in all, right? Does a pretty good job of recovering. And this is somewhat a noisy series too. Okay, there is your whirlwind tour through the frequency domain. And like I said, if people are interested in exploring more about this, I would encourage you. Don Percival is he may be retired now at UW, but he has a book that he's written on wavelets that's, I was going to say kind of accessible. Yeah, you got to read each chapter about 6 times and then it will start to sink in. But there are some short courses out and available and Don used to teach one. It was really good. Anyway, just something to keep in mind for you or if you hear somebody talking about, yeah, we're working in the frequency domain, or yeah, you hear somebody talking about Fourier series or spectral analysis, that sort of thing, at least now you've had some exposure to it. So questions from anyone about this?